This video is audio content only. It does not contain any video footage or images. If you are expecting visual content, please be aware. This is intentionally provided in an audio-only format. We recommend listening to the audio rather than watching the screen. Thank you for your understanding. Welcome. Have you ever wondered how scientists determine the age of ancient artifacts, fossils, or geological formations? Today, we're exploring the fascinating world of chronological dating, the scientific methods that allow us to peer back through time and establish when events occurred in Earth's history. From radiocarbon dating to tree rings and beyond, we'll discover how researchers unlock the secrets of the past with remarkable precision. Whether you're curious about archaeology, geology, or simply love understanding how we know what we know, this journey through time's measuring tools promises to be both enlightening and surprising. Let's begin. Chapter 1. The Radiocarbon Revolution. In the late 1940s, archaeologists faced a fundamental problem that had plagued their discipline since its inception. They could dig up magnificent artifacts from ancient civilizations, carefully excavate layer upon layer of human history, and arrange their finds in relative sequences based on which objects lay deeper in the ground than others. But they could not answer the most basic question that anyone might ask about their discoveries. Exactly how old are they? An archaeologist could confidently state that one pottery style was older than another, or that a particular settlement had been abandoned before another was built, but assigning actual calendar years to these events remained frustratingly out of reach. Without this ability to measure time in years, the entire story of human civilization existed in a kind of floating chronology, anchored only to the relatively recent past, where written records provided firm dates. This situation changed dramatically in 1949 when a chemist at the University of Chicago named Willard Libby announced a revolutionary technique that would transform archaeology forever. Libby had discovered a way to determine the age of organic materials by measuring the decay of a radioactive form of carbon. The implications were staggering. For the first time in history, scientists could take a piece of ancient wood, a fragment of bone, or a sample of charcoal from a prehistoric campfire and determine with reasonable precision when the tree had been cut down, when the animal had died, or when the fire had burned. This was radiocarbon dating, and its impact on our understanding of the human past cannot be overstated. The science behind radiocarbon dating is elegant in its simplicity, though the execution requires sophisticated equipment and careful methodology. High in the Earth's atmosphere, cosmic rays constantly bombard nitrogen atoms, occasionally transforming them into a radioactive isotope of carbon known as carbon-14. This radioactive carbon quickly combines with oxygen to form carbon dioxide, which mixes throughout the atmosphere. Every living thing on Earth, whether plant or animal, continuously absorbs this carbon-14 along with ordinary carbon through photosynthesis or through eating other organisms. As long as an organism remains alive, it maintains a constant ratio of radioactive carbon-14 to normal carbon-12 in its tissues, the same ratio that exists in the atmosphere. But the moment that organism dies, whether it is a tree felled for timber, an animal hunted for food, or a person laid to rest in a grave, it stops taking in new carbon. From that instant forward, the carbon-14 already in the tissues begins to decay at a perfectly predictable rate. Steady pacing occurs according to a fixed schedule measured in what scientists call a half-life. For carbon-14, the half-life is approximately 5,730 years. This means that after this period, exactly half of the carbon-14 atoms present at death will have decayed. After another 5,730 years, half of the remainder will have decayed, leaving only 1/4 of the original amount. This process continues inexorably, ticking away like a molecular clock that begins running the instant an organism dies. By carefully measuring how much carbon-14 remains in an ancient sample and comparing it to how much we would expect to find in living tissue, scientists can calculate how long ago death occurred. The mathematics are straightforward. If a piece of ancient wood contains half the carbon-14 found in modern wood, it is approximately one half-life old, or about 5,730 years. If it contains 1/4 of the expected amount, it is roughly 2 half-lives old, or about 11,460 years. When Libby first published his method in 1949, the archaeological community responded with a mixture of excitement and profound skepticism. The technique seemed almost too good to be true, and indeed, the early results produced some puzzling contradictions with established archaeological chronologies. The ancient city of Jericho yielded dates suggesting settlement around 7,000 years before the present, some 1,500 years earlier than archaeologists had previously believed possible. Sites in Europe associated with early agriculture were coming back with dates roughly 1,000 years older than the accepted wisdom of the time. These discrepancies made many archaeologists question whether the entire method was fundamentally flawed. Libby himself worked to validate the technique by dating samples of known age, including wood from the tombs of Egyptian pharaohs whose reigns could be dated historically. When the radiocarbon dates matched the historical chronologies, confidence in the method began to grow. Early radiocarbon dating faced technical challenges, including contamination, atmospheric variations, and interpretive issues, such as the old wood problem, where timber from long-lived trees could give misleading dates because the innermost rings might be centuries older than when the tree was actually felled. These difficulties were gradually overcome through improved laboratory protocols and the development of calibration methods that accounted for past fluctuations in atmospheric carbon-14 levels, primarily through comparison with tree ring chronologies. By the mid-1950s, major archaeological institutions were establishing radiocarbon laboratories, and by the 1960s, the technique had become standard practice. The development of accelerator mass spectrometry in the late 1970s and 1980s marked another quantum leap. Traditional radiocarbon dating had required relatively large samples because it worked by counting the actual radioactive decay events occurring in the sample over a period of time. AMS technology changed the game entirely by counting individual atoms of carbon-14 directly rather than waiting for them to decay. This meant that much smaller samples could be dated, sometimes as single grain of rice. Suddenly, precious artifacts that could never have been destroyed for traditional radiocarbon dating could be sampled and dated with minimal damage. Tiny fragments of the Dead Sea Scrolls could be dated. Individual seeds from archaeological sites could be analyzed. Even threads from ancient textiles became datable. The impact on archaeology was transformative, what the archaeologist Colin Renfrew termed the first radiocarbon revolution. Entire frameworks for understanding prehistory had to be reconsidered in light of the new chronologies that radiocarbon dating revealed. Perhaps nowhere was this impact more dramatic than in European archaeology. Before radiocarbon dating, the standard interpretation held that civilization had originated in the ancient Near East, in Mesopotamia and Egypt, and then gradually spread westward into barbarian Europe through trade contacts and the diffusion of ideas. This diffusionist model seemed logical. The great civilizations of Egypt and Mesopotamia had writing systems that allowed their histories to be dated with reasonable accuracy. European prehistoric societies had no writing, so their chronologies could only be estimated by reference to contacts with the literate civilizations to the east. When a particular type of artifact appeared in both Egypt and Europe, and the Egyptian example could be dated through historical records, archaeologists assumed the European version must be younger, having been inspired by or copied from the Eastern prototype. Radiocarbon dating demolished this comfortable assumption. The technique revealed that many supposedly derivative European accomplishments actually predated their supposed Mediterranean prototypes. Megalithic tombs in Western Europe, massive stone monuments requiring considerable organizational skill and labor, turned out to be older than the pyramids of Egypt. The Great Passage tomb at Newgrange in Ireland, with its sophisticated astronomical alignments, was built around 3,200 years before the present, making it older than Stonehenge and predating the Egyptian pyramids by several centuries. Agricultural settlements in southeastern Europe dated to periods before farming was thought to have spread from the Near East.
These revelations forced a fundamental rethinking of European prehistory. Rather than passive recipients of civilization from the East, prehistoric European societies emerged as innovative cultures, developing their own sophisticated technologies and social organizations independently.
The revolution extended far beyond Europe. In the Americas, radiocarbon dating established firm chronologies for the rise and fall of civilizations that had left no written records. The mysterious Nazca lines of Peru, giant geoglyphs etched into the desert, could be dated through organic materials found at the sites, revealing that these enigmatic creations spanned a period from roughly 2,000 to 1,500 years ago. In North America, the technique documented the spread of agriculture from Mexico northward and revealed the sophisticated urban planning of sites like Cahokia, where a vast pre-Columbian city flourished near modern-day St. Louis around 1,000 years ago, with a population that may have rivaled London at the time. Before radiocarbon dating, the scale and antiquity of such achievements were largely unrecognized or dismissed. The method has resolved long-standing historical mysteries and settled contentious debates that had raged for decades. The famous Turin shroud, claimed by some to be the burial cloth of Jesus, was dated through radiocarbon analysis in 1988 to the medieval period, between the 13th and 14th centuries, definitively ruling out a first-century origin. The analysis of Kennewick Man, a controversial skeleton found in Washington state in 1996, revealed through radiocarbon dating that the remains were approximately 8,600 years old, making them among the oldest and most complete skeletons ever found in the Americas, and sparking important discussions about ancient human migration patterns. The technique confirmed that the extinction of woolly mammoths on remote Wrangel Island in the Arctic Ocean occurred as recently as 4,000 years ago, long after these creatures had vanished from the mainland, documenting a relict population that survived into the age of the pyramids. Archaeological excavations today routinely incorporate radiocarbon dating into their research design. Excavators carefully collect charcoal samples from ancient hearths, seeds from storage pits, and bone from burials, meticulously documenting their stratigraphic position before sending them to specialized laboratories for analysis. The resulting dates anchor the occupation of sites to specific time periods, allowing archaeologists to track the spread of technologies, the movement of peoples, and the timing of environmental changes with unprecedented precision. A site that might once have been vaguely attributed to the Bronze Age can now be pinpointed to specific centuries, allowing comparison with sites thousands of miles away and revealing patterns of cultural connection and change that would otherwise remain invisible. For all its power, radiocarbon dating does have limitations. The method works only on organic materials, things that were once alive. Stone tools, pottery, and metal objects cannot be directly dated unless they contain organic residues. The technique becomes increasingly imprecise for very old materials. Beyond about 50 to 60,000 years, the amount of remaining carbon-14 becomes too small to measure accurately with current technology. This means that radiocarbon dating, despite its revolutionary impact, cannot reach back to the earliest chapters of human evolution, which unfolded over millions rather than thousands of years. For those deeper time periods, other dating methods are required. Yet, within its effective range, radiocarbon dating has fundamentally altered how we understand the human past. By providing a reliable method for measuring time in years, it transformed archaeology from a discipline that could only arrange events in relative sequence into one that could build precise chronologies spanning millennia. Before radiocarbon dating, archaeologists debated whether human civilization was 5,000 or 10,000 years old, whether prehistoric monuments were separated by centuries or millennia, whether cultures developed independently or always through diffusion from a few centers of innovation. After radiocarbon dating, these questions could be answered with data rather than speculation. The introduction of this technique represents one of those rare moments when a single scientific innovation reshapes an entire field of study.
Willard Libby's development of radiocarbon dating earned him the Nobel Prize in Chemistry in 1960, recognition not just of a clever laboratory technique, but of a discovery that opened new windows into human history. Today, more than 70 years after Libby's initial announcement, radiocarbon dating remains an indispensable tool in archaeology, continually refined and improved, but still fundamentally based on the elegant principle he discovered, that the atoms within once living things carry within them an atomic clock, ticking away the centuries, waiting for science to learn their message.
As the 19th century progressed, geologists used these principles to construct an increasingly detailed picture of Earth's history. They recognized that certain major changes in fossil assemblages marked the boundaries between great eras of Earth's past. They named these eras based on the forms of life preserved in their rocks: the Paleozoic, meaning ancient life, for the age of trilobites and early fish; the Mesozoic, meaning middle life, for the age of dinosaurs; and the Cenozoic, meaning recent life, for the age of mammals that continues to the present. This geologic timescale allowed scientists to place events in chronological order, but the scale remained stubbornly relative. Geologists could say that the Mesozoic preceded the Cenozoic, but they could not say how long either era had lasted or how many years ago they had occurred. The very thickness and complexity of the geologic record increasingly strained credibility in the biblical chronology. How could layers of rock thousands of feet thick, deposited one grain at a time as sediment settled from ancient oceans, have accumulated in just a few thousand years? The conflict between geological evidence and biblical chronology created fierce intellectual battles in the 19th century. Catastrophists, led by figures like Georges Cuvier, attempted to preserve compatibility with biblical accounts by proposing that Earth's history had been shaped by a series of violent catastrophes, perhaps including Noah's flood, that accomplished in days or weeks what would normally require millions of years. These catastrophes, they argued, had destroyed entire populations of organisms, explaining the extinctions visible in the fossil record, and had deposited thick sequences of rock layers almost instantaneously. James Hutton, a Scottish natural philosopher, championed the opposing view that came to be called uniformitarianism. In the late 1700s, he proposed that the same slow processes observable today had been operating throughout Earth's history, shaping landscapes, depositing sediments, and building mountains over immense spans of time. Hutton could see no evidence of a beginning or prospect of an end in the rock record he examined. His follower, Charles Lyell, developed these ideas further in his monumental Principles of Geology, arguing that understanding the present was the key to understanding the past. If rivers today deposit sediment slowly, then ancient sedimentary rocks must have formed the same way, grain by grain, over enormous durations. The implications were inescapable. Earth must be vastly older than 6,000 years, perhaps incomprehensibly ancient. But without a reliable method for measuring the actual age of rocks in years, these debates remained largely unresolvable. Both sides could point to evidence supporting their views, but neither could provide definitive proof. The breakthrough came from an entirely unexpected direction: the discovery of radioactivity in the final years of the 19th century. Henri Becquerel's 1896 discovery that certain elements spontaneously emit radiation opened up entirely new possibilities for measuring time. Scientists quickly realized that radioactive elements decay at perfectly predictable rates, transforming themselves from unstable parent isotopes into stable daughter products according to fixed schedules that nothing could alter. Temperature, pressure, chemical reactions, none of these affected the rate of radioactive decay. Each radioactive isotope had its own characteristic half-life, the time required for half of the parent atoms to decay into daughter atoms. This process continued inexorably, like a clock that began ticking the moment a rock crystallized from molten magma, and that nothing could reset or stop.
In 1907, Bertram Boltwood proposed using the decay of uranium into lead as a method for dating ancient rocks. Uranium-238, the most abundant isotope, has a half-life of approximately 4.5 billion years. This extraordinarily long half-life makes it perfect for dating the oldest rocks on Earth. By measuring the ratio of uranium to lead in a mineral sample and knowing the decay rate, geologists can calculate how long ago that mineral crystallized. The mathematics are conceptually simple. If a rock started with pure uranium and now contains equal amounts of uranium and lead, one half-life has elapsed. The development of uranium-lead dating revolutionized geology. For the first time, geologists could assign actual ages in years to ancient rocks rather than simply placing them in relative order. The results were staggering and completely demolished any possibility of reconciling the geologic record with a 6,000-year-old Earth. Rocks from deep in the continental crust yielded ages of billions of years. The oldest minerals ever found, tiny crystals of zircon from Western Australia, dated to about 4.4 billion years ago. Even these ancient survivors were not the original crust of the Earth, but had formed from the remelting of still older rocks.
Steady pacing, scientific credibility with approachable warmth. What made these extraordinary ages compelling was not any single measurement, but the convergence of multiple independent methods, all pointing to the same conclusions. Other radiometric techniques proved equally powerful for dating ancient materials. Potassium-argon dating, measuring radioactive decay over billion-year timescales, proved essential for dating ancient volcanic rocks. Rubidium and strontium dating provided yet another independent check, with a half-life of about 49 billion years. Each of these methods relies on different elements, different minerals, and different chemical processes, yet when applied to the same rocks, they yield consistent results. A granite outcrop in Canada might be dated by uranium-lead in its zircon crystals, by rubidium-strontium in its mica, and by potassium-argon in its feldspar, and all three methods would converge on the same age within experimental uncertainty. This concordance of ages from multiple independent techniques provides the most powerful confirmation that the methods are measuring real time and not producing meaningless numbers. But how old is the Earth itself? The planet's original crust has long since been recycled by plate tectonics, subducted into the mantle, and remelted. The oldest rocks preserved on the continents date to about 4 billion years, but these already represent a complex geology with evidence of earlier events. The Earth must be older still, but how could its age be determined if no rocks from the original formation survive? The answer came from an unexpected source: meteorites. These chunks of rock and metal, remnants from the formation of the solar system, have been falling to Earth throughout history. Unlike Earth's surface rocks, meteorites have not been recycled by geological processes. They preserve a record of the solar system's earliest moments. When scientists applied uranium-lead dating and other radiometric techniques to meteorites from different parts of the solar system, they found consistent ages clustering around a single date: 4.54 billion years. This date represents the time when solid material first began condensing from the solar nebula, the cloud of gas and dust from which the sun and planets formed. The Earth, forming from the same cloud of material at the same time, must have the same age. Lunar rocks brought back by Apollo astronauts confirmed the pattern, yielding ages consistent with a solar system that solidified 4.5 billion years ago. This figure, 4.54 billion years, represents one of the great triumphs of 20th century science. The journey from Diogo Cau's confident inscription of year 6,685 to the modern determination of Earth's true age required overturning centuries of accepted wisdom. It demanded that scientists develop entirely new ways of thinking about time and entirely new methods for measuring it. The precision is remarkable, determining the age of the planet to within about 1%, an uncertainty of only about 50 million years. The age has been confirmed by multiple independent dating methods applied to meteorites, lunar samples, and Earth's oldest surviving rocks. These converging lines of evidence leave no reasonable doubt.
A 4.5 billion-year-old Earth provided ample time for the slow processes that geologists observed. Mountain ranges could rise and erode away multiple times. Continents could drift across the globe. The vast sequences of sedimentary rocks visible in places like the Grand Canyon, each layer representing a distinct environment and time period, now made perfect sense. The Great Unconformity and other gaps in the rock record could represent hundreds of millions of years without straining credibility. Paleontologists gained time enough for evolution to transform simple single-celled organisms into the extraordinary diversity of life visible in the fossil record and living today. The vast depth of geological time, measured in billions of years, revolutionized human understanding of our place in the universe. We live not on a young world specially created for humanity, but on an ancient planet whose story stretches back through billions of years before the first humans appeared. The radiometric dating techniques that revealed this deep time continue to shape our understanding in practical ways. Mining geologists use radiometric dates to understand the processes that concentrated valuable ore deposits, predicting where undiscovered resources might lie. Petroleum geologists apply these methods to understand the thermal history of sedimentary basins, crucial information for predicting where oil and gas might have formed and been trapped. Planetary scientists apply the same techniques to meteorites and samples from other worlds, building chronologies for the entire solar system and revealing that the heavily cratered surfaces of the Moon and other bodies record a violent early bombardment that tapered off about 3.8 billion years ago, just as life was emerging on Earth. The story of how science established Earth's true age represents more than just a technical achievement. It illustrates the power of converging lines of evidence, of multiple independent methods, all pointing to the same conclusion. It demonstrates how scientific understanding can overturn long-held beliefs, even beliefs embedded in cultural and religious traditions, when the evidence becomes overwhelming. The narrow chronology that satisfied scholars in the 17th century has given way to a vastly deeper understanding of time. This expansion of temporal horizons ranks among the great revolutions in human thought, comparable to the realization that Earth orbits the Sun rather than standing at the center of creation. Radiometric dating gave us the key to reading Earth's story, written in stone across billions of years. Chapter 3. Lucy, Neanderthals, and Coastal Foragers. The story of human evolution presented scientists with a chronological puzzle unlike any other in archaeology or geology. While geologists could date ancient rocks billions of years old, and archaeologists could precisely date artifacts from historical civilizations, the crucial period when our ancestors diverged from other primates and began the long journey toward becoming modern humans fell awkwardly between these two extremes. The bones and stone tools left by early humans were far too old for radiocarbon dating, which reaches back only about 50,000 years, yet they were far too young and too rare to be easily dated by the methods geologists used on common rocks. Moreover, fossils themselves typically cannot be directly dated. A bone lying in sediment for millions of years loses its original organic chemistry, becoming effectively a rock replica of the original structure. Scientists needed indirect methods, ways to date the geological context surrounding fossils, even when the fossils themselves resisted analysis. The development of these techniques revolutionized our understanding of human origins, revealing not just when our ancestors lived, but where they traveled and how they adapted to changing environments. The breakthrough for dating early human evolution came from a fortunate geological circumstance. Many of the most important early human fossils have been found in the East African Rift Valley, a vast geological fracture stretching thousands of miles from Ethiopia to Mozambique. This region has been volcanically active for millions of years, and volcanic eruptions periodically blanketed the landscape with layers of ash. These ashfalls preserve the landscape of the moment, burying everything beneath them like a geological snapshot. Animals that died and were fossilized in stream sediments or lake beds became sandwiched between datable volcanic layers. The ash itself contains minerals, particularly potassium-bearing crystals, that can be dated using potassium-argon techniques. When volcanic minerals crystallize from molten lava, any argon gas escapes into the atmosphere, setting the radioactive clock to 0. From that moment, radioactive potassium-40 within the crystals begins decaying into argon-40, which becomes trapped in the crystal structure. By carefully measuring the ratio of potassium to argon, scientists can determine when the volcanic eruption occurred and, by extension, bracket the age of fossils found between ash layers. Later refinements produced argon-argon dating, which offers improved precision and can date smaller samples, making it particularly valuable for rare volcanic minerals associated with fossil sites.
Steady pacing, scientific credibility with approachable dating techniques allowed scientists to establish the age of Lucy, perhaps the most famous early human ancestor ever discovered. Found in Ethiopia in 1974 by paleoanthropologist Donald Johanson and his team, Lucy represents a remarkably complete skeleton of Australopithecus afarensis, an early hominin that walked upright but retained many ape-like features. The skeleton itself could not be directly dated, but it lay within sedimentary deposits sandwiched between volcanic ash layers. By dating these ash layers above and below the fossil site using potassium-argon methods, scientists determined that Lucy lived approximately 3.2 million years ago. The precision of this date depends on the clarity of the stratigraphic relationships and the quality of the volcanic minerals analyzed, but the method provided a definitive answer to a question that would have been impossible to address just a few decades earlier. The dating of Lucy and similar fossils required painstaking geological work. Researchers must carefully map the extent and sequence of volcanic ash layers across a region, sometimes tracking individual eruptions across dozens of miles of eroded landscape. They must document the stratigraphic position of fossils relative to these datable markers, ensuring that later geological processes, like erosion or landslides, have not disturbed the original sequence. The principle of superposition, the simple idea that lower layers are older than those above them, remains fundamental, but its application in complex geological terrains requires careful analysis. Each volcanic ash layer represents a brief moment in geological time, an eruption that might have lasted hours or days. The sediments between ash layers might represent thousands or hundreds of thousands of years of gradual accumulation. By dating multiple ash layers in sequence, scientists can construct a chronology for an entire region, creating a framework into which new fossil discoveries can be slotted. The same potassium-argon dating techniques that revealed Lucy's age have illuminated the entire span of human evolution in Africa. Volcanic ash layers associated with even older hominin fossils push the human family tree back beyond 4 million years. Sites containing the earliest stone tools, simple flakes struck from rocks to create sharp edges, have been bracketed by volcanic dates to about 3.3 million years ago, revealing that tool use emerged surprisingly early in our lineage. These dates transform our understanding of human evolution, from vague speculation into precise science. We know not just that our ancestors evolved in Africa, but when key innovations appeared and how long it took for our lineage to acquire the characteristics that defined humanity.
Yet not all crucial periods in human evolution can be dated with volcanic ash. As humans spread out of Africa into Europe and Asia, they entered regions with different geology, where volcanic markers might be absent or rare. For more recent periods of human evolution, roughly the last 50,000 years, radiocarbon dating becomes applicable, particularly with the development of accelerator mass spectrometry, or AMS, which allows dating of much smaller samples than previously possible. This advancement proved crucial for rare human fossils where researchers could not afford to destroy large amounts of precious bone material. But radiocarbon still leaves a problematic gap for the period between about 50,000 and several 100,000 years ago. During this critical interval, anatomically modern humans were emerging and beginning to spread beyond Africa, encountering other human species, including Neanderthals. Dating this period of interaction required developing additional techniques. Electron spin resonance dating, which measures trapped electrons in tooth enamel and can date materials in the 100,000-year range, helped fill this gap, providing chronologies for sites where neither radiocarbon nor potassium-argon methods could be applied effectively. The story of Neanderthals and their relationship with our own species, Homo sapiens, has been rewritten by advances in dating methods. For decades, scientists debated whether Neanderthals and modern humans ever coexisted or whether Neanderthals had already vanished by the time our ancestors arrived in Europe. The question had profound implications for understanding both human evolution and the fate of the Neanderthals. If the two species overlapped in time and space, they might have interacted, competed for resources, or even interbred. If Neanderthals disappeared before modern humans arrived, their extinction must have resulted from other causes. Radiocarbon dating of Neanderthal bones and artifacts initially suggested that the last Neanderthals survived until about 30 to 40,000 years ago, overlapping with early modern humans in Europe by several thousand years. Scientists developed increasingly rigorous protocols to prevent contamination, which is particularly problematic near radiocarbon's 50,000-year limit. These refined radiocarbon methods, combined with thermoluminescence dating of heated flints and electron spin resonance dating of teeth, revealed a more nuanced picture of the Neanderthal-modern human overlap. In some regions of Europe, the two populations coexisted for several thousand years, occupying nearby territories and likely aware of each other's existence. Archaeological sites in cave systems sometimes show alternating occupations, with Neanderthal artifacts in some layers and modern human artifacts in others, dated by radiocarbon to overlapping time periods. This evidence of prolonged coexistence has been confirmed by genetic studies, showing that Neanderthals and modern humans did indeed interbreed, with most people of non-African descent today carrying 1 to 2% Neanderthal DNA in their genomes. The dates established through multiple dating techniques provide the chronological framework for understanding when and where this interaction occurred.
Perhaps no discovery better illustrates the power of modern dating techniques to illuminate human prehistory than the evidence from Pinnacle Point caves on the southern coast of South Africa. Excavations at these coastal cave sites uncovered massive shell middens, ancient garbage heaps where prehistoric humans discarded the shells of mussels, limpets, and other shellfish they had harvested from the rocky shore. The systematic exploitation of marine resources represents an important development in human cultural evolution, demonstrating sophisticated knowledge of tidal patterns, seasonal availability, and the nutritional value of different species. But when did this behavior begin? Dating the shells and associated materials using multiple techniques revealed that humans had been regularly exploiting marine resources at Pinnacle Point for at least 170,000 years. This date pushed back the evidence for systematic coastal foraging by tens of thousands of years earlier than previously documented, suggesting that coastal resources may have played a crucial role in human survival during climate fluctuations when inland resources became scarce. The dating of Pinnacle Point demonstrates the importance of using multiple independent techniques. Researchers dated organic materials using radiocarbon for the more recent deposits, applied thermoluminescence to heated stones from ancient hearths, and analyzed the rate of sediment accumulation in the cave deposits. Each method provided corroborating evidence, building confidence in the chronology. When radiocarbon dates on charcoal from hearths, thermoluminescence dates on fire-heated stones, and uranium series dating of cave formations all indicated the same age range for the earliest shell middens, scientists could trust that they had accurately determined when coastal foraging began. This principle of convergence, where multiple independent lines of evidence point to the same conclusion, provides the strongest foundation for scientific confidence in any chronology.
The coastal foragers of Pinnacle Point lived during a period of significant climate instability in Africa. By correlating the dates established for human occupation with climate records from ocean sediment cores and ancient lake beds, researchers determined that the intensive use of marine resources coincided with periods when inland areas would have been particularly arid. The rocky coastline, with its reliable supply of shellfish renewed by every tide, provided a refuge when other food sources failed. This pattern suggests that the ability to exploit diverse food sources, including marine resources that other human species rarely used, may have been one of the innovations that allowed our ancestors to survive environmental challenges that drove other lineages to extinction.
Understanding human migration patterns helps modern scientists track the spread of genetic traits through populations, information crucial for medical research and understanding disease susceptibility. The methods developed for dating human evolution have also been adapted to track changes in animal populations over millennia, information vital for managing endangered species and understanding how populations respond to climate change. By establishing precise chronologies for the appearance and extinction of species, scientists can calculate how quickly evolution operates under different conditions, helping biologists predict how quickly species might adapt to changing environments today. The chronology of human evolution, from the 3.2-million-year-old Lucy to Neanderthals disappearing roughly 30,000 years ago, to the ancient coastal foragers of Pinnacle Point 170,000 years ago, provides a framework for understanding our species' journey. These are not merely abstract numbers, but anchor points in the human story, moments when we can say with confidence that our ancestors were in a particular place, using particular technologies, adapting to particular environments. Each new date refines our understanding, sometimes confirming previous hypotheses, sometimes forcing complete reconsideration of how human evolution proceeded. The methods continue to improve, with new techniques emerging and established ones becoming more precise and applicable to a wider range of materials. What remains constant is the fundamental importance of chronology to human knowledge. Without accurate dates, we have fossils and artifacts, but no story connecting them. With precise chronologies derived from sophisticated dating methods, those scattered bones and stone tools transform into chapters of the human narrative, revealing where we came from, illuminating how our ancestors survived challenges not unlike those we face today. Chapter 4: How Tree Rings Reveal Time. As discussed in Chapter 1, radiocarbon dating faced a critical challenge when scientists discovered that atmospheric carbon-14 levels had fluctuated over time, requiring calibration to convert radiocarbon measurements into accurate calendar dates. The solution to this problem came from an unexpected source, a dating method originally developed not for archaeology, but for understanding climate patterns and solar activity in the American Southwest. Trees growing in temperate climates add a new ring of wood beneath their bark each year. During the growing season, typically spring and summer, trees produce large light-colored cells. As growth slows in late summer and fall, they produce smaller, darker cells. This creates a visible boundary between each year's growth, a ring that can be counted like the pages of a book. The brilliant insight that transformed simple ring counting into a sophisticated dating technique came from astronomer Andrew Ellicott Douglas, working in Arizona in the early 20th century. Douglas was interested in sunspot cycles and wondered whether solar activity might influence Earth's climate. He reasoned that if climate varied with sunspot cycles, trees might record these variations in their growth rings. Wide rings would indicate favorable growing conditions with adequate rainfall, while narrow rings would mark years of drought. As Douglas examined cross-sections of trees, he discovered something remarkable. Trees of the same species growing across a wide geographical area and exposed to the same weather patterns produced similar sequences of ring widths.
A distinctive pattern of wide and narrow rings would appear in tree after tree across an entire region. This meant that ring patterns could be matched between different trees, like fingerprints, a process Douglas called cross-dating. If you had a tree of known age, perhaps cut down in a year recorded by historical documents, you could count back through its rings to assign calendar years to each ring. Then, if you found an older dead tree, you could match the outermost rings of the older specimen with the innermost rings of the younger tree where they overlapped in time. By linking together overlapping sequences from progressively older trees, Douglas realized he could build a continuous chronology stretching back far beyond the lifespan of any individual tree. This technique reached astonishing fruition in the American Southwest, where exceptionally dry conditions preserved wood for millennia. Ancient wooden beams from Pueblo dwellings, timber from long-abandoned villages, and even charred logs from archaeological sites could be cross-dated against living trees and against each other. By the time Douglas published his breakthrough findings in 1929, he had constructed a tree ring chronology extending back more than 2,000 years. Today, the master chronology for the American Southwest reaches back to 322 BCE, an unbroken sequence of annual markers spanning more than 2,300 years. Every single ring in this sequence has been assigned a specific calendar year through careful cross-matching of thousands of individual samples. The precision of dendrochronology is genuinely extraordinary. Unlike radiocarbon dating, which provides dates with uncertainties of decades or centuries, tree ring dating can identify the exact year, sometimes even the exact season, when a tree was cut down. If a wooden beam still has its bark attached, the outermost ring shows the last year of growth, pinpointing when the tree was felled. Even without bark, if the outermost ring shows only partial formation, indicating the tree was cut mid-growing season, dendrochronologists can narrow the date to a specific season of a specific year. This level of precision transformed archaeology in regions where wood preservation allowed the technique's application. Perhaps no application demonstrates dendrochronology's power more dramatically than the dating of Viking ships. When archaeologists excavate ship burials or recover sunken vessels from Scandinavia's fjords and harbors, they often find wood remarkably well preserved by waterlogged conditions or burial in clay. These ships, magnificent expressions of Viking craftsmanship and seafaring capability, can be dated with extraordinary precision through their timber. In Northern Europe, dendrochronologists have constructed master chronologies for oak extending back thousands of years by cross-matching archaeological samples with progressively older material. When a Viking ship's planks or frames are analyzed, their ring patterns can be matched to this master chronology, revealing exactly when the trees were felled to build the vessel. This precision has resolved historical questions that written records left ambiguous. A particular ship burial might be associated, through artifacts, with a specific Viking chief known from saga accounts, but the sagas were often written centuries after the events they described, and their chronology could be uncertain. Tree ring dates provide definitive answers, confirming or refuting historical associations, and sometimes revealing surprising patterns. Analysis of multiple ships has shown that Viking shipwrights sometimes used timber from trees felled years or even decades apart, suggesting they stockpiled wood or recycled timbers from older vessels. Individual planks in a single ship might date to different years, telling stories of repair and modification throughout a vessel's working life. Dendrochronology has also proven invaluable for dating medieval buildings across Europe. Churches, castles, and houses built with timber frames contain roof beams and structural timbers that preserve centuries of tree ring data. By sampling wooden elements from historical structures and matching their patterns to regional master chronologies, architectural historians can determine construction dates with precision impossible through historical documents alone. A medieval church might have been enlarged or rebuilt multiple times over centuries. Dendrochronology can date each phase of construction by analyzing timbers from different parts of the structure, revealing the building's evolution in precise chronological detail.
The technique even records volcanic eruptions with remarkable clarity. When a massive eruption ejects vast quantities of ash and sulfur dioxide into the stratosphere, the resulting veil of particles blocks sunlight and cools global temperatures. Trees respond to these sudden environmental shifts with distinctive growth anomalies. An eruption year might produce an unusually narrow ring, as reduced sunlight and cooler temperatures suppress growth. The following year or two often show similarly stressed growth as the atmospheric effects persist. By examining tree ring patterns from multiple sites around the world, dendrochronologists can identify years when volcanic eruptions affected global climate. One of the most famous examples involves the eruption of Iceland's Laki volcano in 1783. Trees across Europe and North America show severely suppressed growth for 1783 and 1784, recording the climatic impact of this eruption that produced widespread famine and was documented in historical accounts. For more ancient eruptions that occurred before written records, tree rings provide crucial evidence. Mysterious climate anomalies recorded in ice cores or geological deposits can sometimes be dated by matching them to distinctive tree ring patterns showing eruption signatures. These applications demonstrated dendrochronology's extraordinary precision and reliability, which made the technique invaluable for solving radiocarbon's calibration problem. The process works by taking wood samples whose ages are precisely known from tree ring counting and measuring their radiocarbon content in the laboratory. If atmospheric carbon-14 levels had remained constant through time, as Libby originally assumed, a sample from a tree that died exactly 3,000 years ago should contain a specific, predictable amount of carbon-14 based on known radiocarbon decay rates. But when scientists performed these measurements, they discovered systematic differences. Wood from certain periods contained more carbon-14 than expected based on its tree ring age, while wood from other periods contained less. These variations reflected real changes in atmospheric carbon-14 production over time, likely caused by fluctuations in cosmic ray intensity reaching Earth, changes in the planet's magnetic field strength, which shields against cosmic rays, and alterations in how carbon cycles between the atmosphere and oceans. The construction of calibration curves required analyzing thousands of tree ring-dated samples spanning millennia. Scientists would take wood from a ring dated, for instance, to exactly 2847 BCE by dendrochronology, measure its radiocarbon content, and plot the relationship between the known calendar age and the measured radiocarbon age. Repeated thousands of times with samples from different periods, this process revealed a complex, non-linear relationship. The resulting calibration curves show how to convert raw radiocarbon ages into accurate calendar dates. These curves reveal that radiocarbon years and calendar years do not correspond one-to-one. A raw radiocarbon age of 3,000 years might correspond to a calendar age anywhere from about 2,800 to 3,200 years ago, depending on exactly which period the sample came from. During some periods, the calibration curve is relatively flat, meaning samples with quite different calendar ages might yield similar radiocarbon ages, creating ambiguity. During other periods, the curve is steep, allowing more precise calendar age determination. Without tree ring calibration, these complexities would make radiocarbon dating far less useful. With calibration, scientists can convert radiocarbon measurements into reliable calendar dates with well-understood uncertainties. Modern calibration curves, still based fundamentally on tree ring data, but extended with other methods like cave formations and ocean sediments for periods beyond the tree ring chronologies, allow radiocarbon dating to achieve its full potential.
The real-world applications of dendrochronology extend far beyond archaeology and radiocarbon calibration. Climate scientists use tree rings as detailed archives of past environmental conditions. The width and density of rings record temperature and moisture availability year by year, creating climate records stretching back millennia in some regions. These records help scientists understand natural climate variability, providing context for modern climate change. By examining how climate varied before human influence, researchers can better distinguish natural fluctuations from anthropogenic changes. Tree ring records from the American Southwest, for instance, reveal multi-decade droughts far more severe than anything experienced in the historical period, information crucial for water resource planning in a region where drought is an ever-present concern. Art historians and museum curators employ dendrochronology to authenticate paintings and wooden sculptures. A painting on a wooden panel can be dated by analyzing the tree rings in the panel itself. If a painting supposedly created by a Dutch master in 1650 yields wood that was not cut until 1700, the painting must be a later copy or a forgery. This application has exposed fraudulent attributions and confirmed the authenticity of disputed works. The technique requires only a tiny sample, sometimes just a few millimeters drilled from the edge of a panel, making it practical for analyzing valuable artworks.
Steady pacing, scientific credibility with approachable warmth. Construction engineers and building conservators use tree ring analysis to understand the stability and history of historic wooden structures. Knowing the exact age of structural timbers helps in planning conservation work and understanding how buildings have weathered over centuries. Patterns of decay and insect damage can be correlated with climate records from the same tree's rings, helping predict where future deterioration might occur. In Japan, where traditional wooden temples and shrines are national treasures, dendrochronology helps guide restoration projects by revealing the original construction dates and identifying which timbers are original and which were replaced during past repairs. Forensic scientists have even applied dendrochronology to criminal investigations. In cases involving illegal logging, tree ring analysis can determine when a tree was cut, potentially linking seized timber to specific theft events. Environmental crimes, such as cutting protected trees, can be dated through ring analysis of stumps or remaining branches. The precision of the method, potentially identifying the exact year or even season of cutting, can provide crucial evidence in prosecutions. The method continues to evolve and expand geographically. While the American Southwest and Northern Europe have the longest and most thoroughly developed chronologies, dendrochronologists are building master sequences for regions around the world. Each new region requires careful work to identify suitable species, locate ancient wood samples, and develop cross-dating techniques appropriate to local conditions. Tropical regions present particular challenges because many tropical trees do not produce clear annual rings, but even there, some species show distinct growth patterns that can be dated. As chronologies expand and techniques improve, dendrochronology's applications multiply. What makes tree ring dating so powerful is its combination of precision and independence from other methods. Unlike radiocarbon, which requires calibration, or thermoluminescence, which depends on assumptions about past radiation levels, dendrochronology relies simply on counting annual growth increments. The method is self-checking through cross-dating, requiring patterns to match across multiple trees before accepting a sequence. This rigor gives scientists exceptional confidence in dendrochronological dates, confidence justified by the method's success in dating events known from historical records, and its crucial role in calibrating other dating techniques. From Viking ships to volcanic eruptions, from radiocarbon calibration to climate reconstruction, the humble tree ring has proven to be one of archaeology's and environmental science's most powerful chronological tools, transforming patterns of light and dark wood into precise windows on the past.
Chapter 5. When dating methods disagree. The scientific dating methods that have revolutionized our understanding of the past share a common characteristic that scientists sometimes wish the public understood better. They are not infallible. Despite the precision implied by dates reported with statistical confidence intervals and plus or minus ranges, dating techniques can and do produce incorrect results. Different dating methods applied to the same material sometimes yield contradictory ages. Samples can be misdated because of unrecognized geological disturbances. Understanding when and why dating methods fail proves just as important as understanding how they work when everything goes right, because these failures reveal the limits of our knowledge and force scientists to develop more rigorous protocols. The history of chronological dating includes not just triumphant revelations, but also embarrassing mistakes, bitter controversies, and the humbling experience of watching confident conclusions collapse under the weight of better evidence. The most vexing problems arise when different dating techniques applied to the same geological context yield contradictory ages, forcing scientists to grapple with the question of which result to trust. At Olduvai Gorge in Tanzania, early attempts to date the famous hominin fossil beds produced a spectacular conflict. Potassium-argon dating of volcanic tuffs suggested ages around 1.8 million years for certain layers, while initial faunal correlations based on evolutionary stages of extinct animals suggested significantly younger ages. The conflict sparked intense debate about whether the potassium-argon dates were reliable or whether the volcanic minerals had been contaminated with older material. Only through extensive additional dating using multiple techniques, including argon-argon dating of individual mineral crystals, did scientists confirm that the potassium-argon ages were correct and the faunal correlations had been based on incorrect assumptions about evolutionary rates. Similar conflicts plague archaeological sites where organic remains suitable for radiocarbon dating occur alongside volcanic materials suitable for potassium-argon methods. At Pamongwe Cave in Zimbabwe, radiocarbon dates on charcoal suggested human occupation around 30,000 years ago, while potassium-argon dates on volcanic materials in similar stratigraphic positions initially yielded ages closer to 50,000 years. The discrepancy of 20,000 years could not be dismissed as minor analytical uncertainty. Resolving such conflicts requires detective work, combining geological field observations with careful reconsideration of laboratory results. Scientists must examine stratigraphic relationships in detail, looking for evidence of disturbance or redeposition. They date additional samples using multiple methods, searching for consistent patterns that might reveal which initial date was anomalous.
Geological processes create numerous ways that dated materials can become separated from the archaeological or paleontological remains they are supposed to date. Bioturbation, the mixing of sediments by burrowing organisms, can move materials vertically through deposits by tens of centimeters or more. Earthworms, rodents, insects, and plant roots all disturb stratification, carrying younger materials into older layers and vice versa. A charcoal fragment from a fire that burned 5,000 years ago might be carried downward by earthworm activity into a layer that is actually 10,000 years old. Dating that charcoal would then produce an age 5,000 years too young for the layer containing it. Archaeologists working in regions with active bioturbation must carefully assess whether the vertical positions of dated samples actually represent their original context or whether mixing has occurred. Unconformities, gaps in the depositional record representing periods when no sediments accumulated or when previously deposited sediments eroded away, create another source of confusion. Two layers that appear adjacent in a stratigraphic sequence might actually be separated by thousands of years of missing time. A volcanic ash dated to 1 million years ago might lie directly atop sediments dated to 1.2 million years ago, with the intervening 200,000 years completely absent from the record. Without recognizing the unconformity, interpreters might assume continuous deposition and reach false conclusions about rates of evolution or climate change. Identifying unconformities requires careful field observation, looking for erosional surfaces, abrupt changes in sediment characteristics, or dating patterns that reveal temporal gaps.
Redeposition of materials by water, wind, or slope processes create situations where everything has been correctly dated, but the dates do not mean what they seem to mean. A volcanic ash layer might be dated to one age, accurately measuring when the eruption occurred, while the ash layer's position in a stratigraphic sequence no longer represents the eruption's timing because wind or water transported the ash particles and redeposited them years or even centuries after the eruption. River systems are particularly prone to redepositing materials, reworking older sediments, and mixing them with younger deposits. A river cutting through ancient deposits might pick up charcoal from a fire that burned 8,000 years ago and redeposit that charcoal in modern floodplain sediments. Dating the charcoal would accurately reveal when the fire burned, but misleadingly suggest that humans occupied the floodplain 8,000 years ago, when in fact the modern floodplain had not yet formed. Geological processes can reset radiometric clocks long after rocks first formed, leading to dates that are accurate measurements of the resetting event, but misleading if interpreted as the rock's original formation age. Metamorphism, the transformation of rocks through heat and pressure deep within the Earth's crust, can drive argon gas out of potassium-bearing minerals, resetting the potassium-argon clock to zero. The Grenville province of eastern Canada contains rocks whose original crystallization occurred over 1 billion years ago, but many yield potassium-argon ages of only about 100 million years because Cretaceous heating partially reset their radiometric systems. If geologists date such metamorphosed rocks without recognizing the resetting event, they will measure the time since metamorphism, not the original crystallization age. Similarly, rocks heated by nearby igneous intrusions might have their radiometric systems partially reset, yielding ages intermediate between the original formation and the heating event, accurately representing neither. One of the most spectacular failures in the history of archaeological dating involved a supposed ancient human skull found in the Piltdown quarry in England beginning in 1912. The Piltdown skull appeared to combine a human-like cranium with an ape-like jaw, fitting certain preconceptions about how human evolution should have proceeded, with brain enlargement preceding other anatomical changes. For decades, scientists accepted the Piltdown fossils as genuine evidence of an early human ancestor, despite some nagging doubts about the specimen's anatomy and the curious circumstance that no similar fossils turned up anywhere else in the world. The bones were presumed to be of Pleistocene age, hundreds of thousands of years old, based on their geological context and the extinct animal fossils found with them. When fluorine dating became available in the 1940s, scientists applied it to the Piltdown bones to verify their antiquity. Fluorine dating measures the amount of fluorine absorbed by buried bones from groundwater, with the assumption that bones buried longer will have absorbed more fluorine. The method revealed a devastating truth. The skull and jaw had very different fluorine concentrations, indicating they were not the same age. The skull had absorbed substantial fluorine, consistent with considerable antiquity, but the jaw had absorbed very little, suggesting it was much younger. Further investigation in 1953, including additional chemical tests and detailed anatomical analysis under better lighting, revealed the Piltdown specimen as an elaborate hoax. Someone had taken a medieval human skull and combined it with a modern orangutan jaw, treating the bones with iron compounds and other chemicals to make them appear ancient and filing the teeth to make the jaw seem more human-like. The differing ages revealed by fluorine dating exposed the fraud, though the perpetrator's identity remains debated. The episode demonstrates both the power of dating methods to reveal truth and the danger of accepting finds that fit preconceived notions too neatly.
The challenge of rewriting history when new dates contradict established chronologies creates tensions in scientific communities. Scholars build careers developing interpretations based on accepted chronologies. Textbooks are written, museum exhibits designed, and public understanding shaped by what seems to be well-established knowledge. When new dating evidence forces reconsideration of these foundations, resistance can be fierce.
The early radiocarbon dates suggesting that European megalithic monuments were older than Egyptian pyramids faced skepticism precisely because they overturned the comfortable diffusionist model where civilization spread from the Near East to barbarian Europe. Stonehenge, the massive passage tomb at Newgrange in Ireland, and the megalithic temples of Malta all yielded radiocarbon dates pushing their construction back to the 4th and 5th millennia before present, making them older than the Egyptian pyramids and contemporary with or earlier than the earliest Near Eastern civilizations. The implications were profound. Monumental construction and sophisticated societies had developed independently in Atlantic Europe rather than being inspired by contact with more advanced civilizations elsewhere. Only when the radiocarbon methodology had been thoroughly vetted and dates confirmed through multiple samples did the archaeological community broadly accept that the previous chronology had been fundamentally wrong. Similar controversies continue today across various fields. Dates that push back the antiquity of human occupation in the Americas challenge long-held models of when and how people first reached the Western Hemisphere. For decades, the Clovis culture, with distinctive spear points appearing around 13,000 years ago, was considered the earliest human presence in the Americas. Sites yielding pre-Clovis dates faced intense skepticism. When Monteverde in Chile produced radiocarbon dates around 14,500 years ago, critics initially claimed the dates must be wrong, perhaps due to contamination, or suggested the dated materials were not actually associated with human artifacts. Meadowcroft Rock Shelter in Pennsylvania yielded dates extending back 16,000 years or more, but these too faced challenges, with some arguing that coal particles in the local geology might have contaminated samples with ancient carbon, making them appear older than their true age. Only as more sites produced similar dates, as dating protocols became increasingly rigorous, and as multiple independent dating methods confirmed the results, did consensus shift toward accepting an earlier human presence. The Page Ladson site in Florida, with mastodon remains showing butchering marks dated to 14,550 years ago, provided confirmation through multiple radiocarbon dates on different materials, all yielding consistent ages. Even now, claims for still earlier occupation, such as dates exceeding 20,000 years at some Brazilian sites, remain contentious. The exact timing and route of first colonization continue to be reshaped by new dates, each requiring careful evaluation and often sparking debate about methodology and interpretation. The real-world applications of understanding dating failures extend across multiple fields. Environmental remediation efforts rely on dating contaminated sediments to identify when pollution began and which parties might be responsible. If a factory contaminated a river with toxic chemicals, dating sediment cores can reveal when contamination started, potentially identifying the responsible party among multiple industrial facilities operating at different times. The Hudson River in New York contains sediments contaminated with PCBs, and establishing when contamination occurred became crucial for determining liability. Dating such sediments requires full awareness of how river dynamics can disturb layering, potentially moving contaminated material into older layers or vice versa through bioturbation and sediment reworking. In legal contexts involving property rights or cultural heritage disputes, dating evidence might prove crucial. Archaeological sites sometimes become subjects of political controversy, with different parties claiming historical precedents based on the antiquity of remains. Dates that favor one narrative over another face intense scrutiny, and any methodological weakness becomes grounds for challenge. In such contexts, the use of multiple independent dating methods provides crucial protection against claims that a single date might be erroneous. When radiocarbon, thermoluminescence, and optically stimulated luminescence all yield consistent ages, challenging the chronology becomes far more difficult. The lessons learned from dating failures has made the entire enterprise more robust. Scientists now routinely date multiple samples from the same context using different methods when possible. They have developed statistical methods for identifying outliers in sets of dates, helping distinguish real patterns from noise introduced by various complications. When multiple radiocarbon dates are obtained from a single archaeological layer, statistical tests can identify which dates fall outside the expected range, potentially indicating contamination or association problems. The chi-square test compares the scatter in a set of dates to what would be expected from measurement uncertainty alone. If the scatter is too large, it suggests the samples are not all the same true age, prompting investigation of which dates might be problematic. Scientists are more cautious about accepting dates that seem anomalous, subjecting such results to additional scrutiny rather than building interpretations around them immediately. The strongest chronologies emerge from multiple lines of evidence, all pointing in the same direction, creating networks of mutually supporting dates that are far more reliable than any individual measurement. At the Denisova cave in Siberia, establishing the chronology of hominin occupation required combining radiocarbon dating, uranium series dating, and optically stimulated luminescence dating across different materials and stratigraphic units, with dozens of dates creating a framework far more reliable than any single technique could provide.
Understanding that dating methods can fail does not undermine their utility, but rather clarifies how they should be used. The methods work remarkably well when applied appropriately to suitable materials in proper geological contexts. They fail when geological history proves more complex than recognized, when materials have been disturbed or redeposited, or when analysts make unwarranted assumptions about what they are dating. Acknowledging these limitations, developing protocols to minimize errors, and building chronologies through multiple independent lines of evidence transforms dating from a simple matter of sending samples to a laboratory into a sophisticated scientific endeavor requiring geological understanding, analytical expertise, and statistical rigor. The dates that emerge from this process, tested against multiple lines of evidence and scrutinized for potential sources of error, provide the chronological framework upon which our understanding of the past is built. They are not perfect, but they are continually improving, and they have transformed our knowledge of human history and Earth's story in ways that would have seemed impossible just a few generations ago. Chapter 6: When Worlds End. When geologists in the 19th century first recognized that the rock record preserved evidence of vanished worlds populated by extinct creatures, they faced a profound mystery. The fossils clearly showed that life on Earth had changed dramatically over time. Trilobites that dominated ancient seas had disappeared entirely. Ammonites with their elegant spiral shells had vanished. Most spectacularly, the dinosaurs that once ruled terrestrial ecosystems had been completely wiped out, leaving behind only their fossilized bones as testament to their former existence. But what had caused these disappearances? Had species simply evolved gradually into new forms, or had something more catastrophic occurred? And perhaps most puzzling of all, when different groups of organisms disappeared from the fossil record, did they all vanish at the same moment in geological time, or did their extinctions occur over millions of years? Early geologists discovered that they could use the principle of faunal succession to identify and correlate rock layers across vast distances. Each period in Earth's history contained unique assemblages of fossils, and these distinctive fossil communities appeared in the same sequence wherever rocks of the appropriate age were found. The appearance and disappearance of specific fossil groups defined the boundaries between geological periods. Reading these boundaries required understanding basic stratigraphic principles. The principle of superposition states that in undisturbed sequences, younger rocks lie above older rocks. Original horizontality tells us that sedimentary layers are deposited in horizontal sheets. Cross-cutting relationships reveal that any geological feature cutting across rock layers must be younger than the layers it cuts. These principles allow geologists to work out the relative sequence of events, but without the ability to date rocks with precision, fundamental questions remained frustratingly unanswerable.
Scientists could observe that dinosaurs disappeared from the rock record at a certain stratigraphic level, but they could not determine whether this disappearance happened suddenly or gradually, nor could they compare the timing of extinctions on different continents to determine whether the event was truly global. Steady pacing, scientific credibility with approachable warmth. The development of radiometric dating techniques in the 20th century transformed the study of mass extinctions from speculation into rigorous science. For the first time, geologists could assign actual ages in years to the boundaries between geological periods and determine whether extinctions had occurred rapidly or slowly. The results revealed that Earth's history included several episodes of truly catastrophic extinctions, when significant percentages of all species on the planet disappeared within geologically brief time periods. The most famous of these events marks the boundary between the Cretaceous and Paleogene periods, an instant in geological time when the dinosaurs and countless other species vanished. This Cretaceous-Paleogene boundary, often abbreviated as the KP boundary, occurs in rock sequences around the world as a distinctive layer separating fossil assemblages. Below this boundary, rocks contain abundant dinosaur remains along with the fossils of many other Cretaceous organisms. Above the boundary, these creatures are entirely absent, replaced by a fundamentally different fauna dominated by mammals and birds. Biostratigraphers recognized that this sudden shift in fossil assemblages represented something extraordinary, but determining exactly what had happened required more than just observing the pattern of disappearances. The first clue that something extraordinary had occurred at the KPG boundary came not from dating, but from geochemistry. In 1980, physicist Luis Alvarez and his son, geologist Walter Alvarez, along with their colleagues, announced a startling discovery. They had been studying the KPG boundary layer in Italy when they decided to measure the concentrations of various elements in the boundary clay. The results showed a dramatic spike in iridium, a rare element on Earth but common in meteorites. The iridium concentration at the boundary was more than 30 times higher than in the rocks immediately above or below. This iridium anomaly appeared not just in Italy, but at KPG boundary sites around the world, suggesting a global event. The Alvarezes proposed a radical explanation. A massive asteroid or comet had struck Earth 66 million years ago, and the impact had injected vast quantities of pulverized rock and extraterrestrial material into the atmosphere. This debris cloud would have circled the globe, eventually settling out as a worldwide layer enriched in iridium and other elements common in asteroids but rare on Earth's surface. The environmental consequences of such an impact would have been catastrophic, potentially causing the mass extinction that eliminated the dinosaurs.
Steady pacing generated intense controversy. Many paleontologists pointed to evidence they interpreted as showing a more gradual decline of dinosaur diversity over the final million years of the Cretaceous. They argued that dinosaurs were already disappearing before any impact occurred, possibly due to climate change, sea level fluctuations, or competition with newly evolving mammals. Some suggested that volcanic eruptions in India, which had produced the vast Deccan Traps lava flows around the same time, might have been the real culprit. The debate became heated, with paleontologists who had spent careers studying dinosaur fossils arguing against physicists and geologists who were proposing an extraterrestrial catastrophe. The question hinged crucially on precise dating. If the Alvarezes were correct, the iridium layer and the extinction horizon should be exactly the same age everywhere they appeared. If extinctions had occurred gradually over millions of years, then the timing should vary from place to place, with some dinosaur populations persisting longer than others. Resolving this question required dating the boundary with unprecedented precision. Scientists applied multiple radiometric dating techniques to rocks associated with the KPG boundary. In many locations, the boundary layer includes shocked quartz grains and small glassy spherules called tektites, both characteristic of meteorite impacts. Volcanic ash layers found just above or below the boundary in various locations could be dated using potassium-argon and the more refined argon-argon methods.
Argon-argon dating, developed as an improvement on the potassium-argon technique, allowed scientists to date individual mineral grains rather than bulk samples, providing greater precision and the ability to detect contamination. These dates converged on a remarkably consistent age, 66 million years ago, with an uncertainty of only a few tens of thousands of years. Fission track dating of volcanic minerals associated with the boundary provided independent confirmation. This method counts microscopic damage trails created by the spontaneous fission of uranium atoms within crystals, and it proved particularly useful for dating the impact-related materials. The precision achieved by combining multiple dating methods was astonishing, given the immense age being measured, and it revealed that the iridium layer appeared at virtually the same moment in geological time across widely separated continents. The extinctions associated with this boundary also occurred synchronously. Dinosaur fossils disappear from the rock record at precisely the level of the iridium anomaly, in location after location, from North America to Europe to Asia. The smoking gun came with the discovery of the impact crater itself. Geophysical surveys in the Yucatan Peninsula of Mexico revealed a buried circular structure more than 100 miles in diameter, a scar so enormous that it had remained hidden beneath younger sediments and the waters of the Gulf of Mexico for 66 million years. This Chicxulub crater, named after a small town near its center, showed all the hallmarks of an enormous impact. Drilling into the crater recovered shocked minerals and impact melt rocks, materials formed only under the extreme pressures and temperatures of meteorite impacts. Radiometric dating of these impact materials yielded ages identical, within experimental uncertainty, to the ages obtained for the global iridium layer and the extinction boundary. The case became overwhelming. A mountain-sized asteroid had struck Earth 66 million years ago, and this impact had triggered the mass extinction that ended the age of dinosaurs. The real-world applications of this discovery extend far beyond satisfying scientific curiosity about prehistoric catastrophes. Understanding that asteroid impacts can cause global mass extinctions has driven efforts to detect and track potentially hazardous asteroids that might threaten Earth today. Space agencies around the world now operate surveys scanning the night sky for near-Earth objects, cataloging their orbits, and assessing their threat potential. The geological evidence from the KPG boundary provides a sobering reminder that such impacts, while rare, can have devastating consequences when they occur. Precise dating of the Chicxulub impact established the timescale over which recovery from such catastrophes occurs. The rock record shows that it took hundreds of thousands to millions of years for ecosystems to fully recover their previous diversity after the KPG extinction. This information helps scientists understand the long-term consequences of biodiversity loss and informs conservation efforts aimed at preventing human-caused extinctions. The techniques developed for dating the KPG boundary have been applied to other mass extinctions throughout Earth's history. The greatest extinction of all occurred at the boundary between the Permian and Triassic periods, approximately 252 million years ago. During this catastrophe, more than 90% of marine species and 70% of terrestrial vertebrate species disappeared. For decades, scientists debated what could have caused such an apocalyptic extinction. Radiometric dating of volcanic rocks associated with the boundary provided a crucial clue. Enormous volcanic eruptions in what is now Siberia had poured out vast quantities of lava, covering an area larger than Western Europe, with basalt flows in some places several miles thick. These Siberian traps, as geologists call them, could be dated using argon-argon methods. The ages obtained matched the timing of the Permian-Triassic extinction within the uncertainties of the measurements. The eruptions had released massive amounts of carbon dioxide, sulfur dioxide, and other gases into the atmosphere. The sulfur triggered acid rain that poisoned terrestrial and freshwater ecosystems. The carbon dioxide drove severe global warming, raising temperatures by perhaps 10 degrees or more. As the oceans warmed, they lost their capacity to hold dissolved oxygen, creating vast dead zones where marine life suffocated. Ocean acidification from absorbed carbon dioxide made it difficult for organisms with calcium carbonate shells to survive. This cascade of environmental disasters, each triggering and amplifying the others, drove the greatest mass extinction in Earth's history. Precise dating revealed that these volcanic eruptions pulsed over several 100,000 years, with the most intense phase coinciding with the peak of the extinction. This timing established a clear link between the volcanism and the biological catastrophe. Understanding this ancient climate disaster provides sobering context for modern concerns about rapid climate change driven by human carbon dioxide emissions. The Permian-Triassic extinction demonstrates that massive, geologically rapid injections of greenhouse gases can trigger catastrophic ecosystem collapse.
Dating techniques have also illuminated smaller-scale but still significant catastrophic events in more recent Earth history. The Younger Dryas stadial, a period of abrupt cooling that interrupted the warming trend at the end of the last ice age, occurred approximately 12,800 years ago. Radiocarbon dating of lake sediments and ice cores pinpointed the timing of this event with precision measured in decades. The cooling happened with shocking speed, with temperatures in some regions plummeting by several degrees within just a few years. The dating evidence shows that this climate reversal had dramatic effects on human populations. Archaeological sites in the Near East show changes in settlement patterns and subsistence strategies that coincide precisely with the Younger Dryas cooling. As wild plant resources became less predictable and abundant game animals moved or declined, human groups experimented with cultivating plants more intensively. Some archaeologists argue that the environmental stress of this period may have provided the crucial impetus for the development of agriculture, forcing innovations in food production that hunting and gathering societies might otherwise have avoided. The ability to date both the climate event and the archaeological evidence with radiocarbon allows researchers to test such hypotheses with precision impossible just decades ago. Tephrochronology, the dating of volcanic eruptions through analysis of ash layers, has become an indispensable tool for understanding both ancient and recent catastrophic events. When volcanoes erupt explosively, they eject vast quantities of ash that can spread over thousands of square miles. Each eruption produces ash with a unique geochemical signature, and these ash layers can serve as time markers that can be traced across wide regions. The massive eruption of Mount Toba in Indonesia, approximately 74,000 years ago, produced ashfalls that have been identified across South Asia and in deep-sea sediment cores from the Indian Ocean. Potassium-argon dating of this ash established its age and revealed that it coincided with a period of apparent population bottleneck in human evolution. Genetic studies suggest that human population sizes crashed around this time, and some researchers have proposed that the Toba eruption, one of the largest volcanic events of the past several million years, may have triggered a volcanic winter that pushed human populations to the brink of extinction. The dating evidence allows scientists to correlate the volcanic event with the genetic and archaeological signals of population stress, though the exact relationship remains debated. The study of mass extinctions and catastrophic events relies fundamentally on the ability to correlate evidence from different locations and determine whether events were truly synchronous or merely appeared simultaneous because of the limited resolution of dating methods. When geologists can demonstrate that an iridium layer in Italy shocked quartz in North America and impact melt rocks in Mexico all formed at the same instant 66 million years ago, the case for a single global catastrophe becomes compelling. Without precise dating, these could be separate events, separated by millions of years, that just happened to occur during the same geological period. The rock record also contains unconformities, gaps in the stratigraphic sequence where rock layers are missing due to erosion or non-deposition. These gaps complicate the reconstruction of catastrophic events, but dating the rocks above and below unconformities allows geologists to bracket the timing of missing intervals and understand what portions of Earth's history have been lost at any given location. The implications extend into realms far beyond academic geology.
Precise dating of past climate catastrophes reveals how rapidly Earth's systems can shift from one stable state to another. The Younger Dryas cooling happened within a human lifetime, faster than societies could easily adapt. Understanding these patterns helps climate scientists identify early warning signals that might precede abrupt changes in modern climate. The dating of mass extinctions has also influenced how conservation biologists think about modern biodiversity loss. The rock record shows that recovery from major extinction events takes millions of years, far longer than human civilization has existed. Once species are lost, the ecosystems they supported cannot be quickly restored. This temporal perspective, revealed through precise dating of ancient events, underscores the urgency of preventing extinctions in the present. Unlike asteroid impacts or massive volcanic eruptions, human-caused extinctions can potentially be prevented through conservation efforts, but only if we act before species disappear entirely. The story of dating mass extinctions exemplifies the power of bringing multiple scientific methods to bear on difficult questions. The KPG extinction could not have been understood through geology alone, or chemistry alone, or dating alone. It required integrating evidence from impact physics, atmospheric science, paleontology, geochemistry, and radiometric dating to build the comprehensive picture we have today. That picture reveals a world fundamentally shaped by catastrophes, where periods of relative stability are punctuated by events that reorganize entire ecosystems in geological instants. Through the precision of modern dating methods, we can measure those instants, understand their causes, and recognize that the world we inhabit today is itself the product of survivals and extinctions stretching back through deep time. The methods that allow us to date when worlds ended also illuminate how new worlds began in their wake.
The development of chronological dating represents one of humanity's greatest intellectual achievements. From radiocarbon dating's revolutionary impact on archaeology to radiometric techniques revealing Earth's 4.5 billion-year history, these methods have fundamentally transformed how we understand our place in time. Tree rings calibrate radiocarbon dates with annual precision. Multiple techniques converge to confirm mass extinctions and climate catastrophes. Human evolution's timeline, once shrouded in speculation, now rests on firm chronological foundations spanning millions of years. These dating methods do more than satisfy curiosity about the past. They reveal how quickly climate can shift, how long ecosystems take to recover from catastrophe, and how our own species navigated environmental challenges throughout prehistory. The precision achieved through decades of refinement allows us to read Earth's story with unprecedented clarity, transforming rocks, bones, and ancient wood into detailed narratives of vanished worlds. Every date is a window into deep time, reminding us that our moment is fleeting in Earth's vast chronicle. Thank you for listening.